Hello everyone, welcome to the Arithmetic Zone. Today we have a video for you guys on the 2012 AP Physics C Mechanics multiple choice set, which is the latest multiple choice set that the College Board has released for this class. Now, AP season is coming up. Exams are in less than a month for most of you. So it's a good time to just review and learn the general structure of an exam, and also just go over some stuff that we may have learned over the year that may have gotten a bit hazy. This is a hard class and a hard test to pass, and for the multiple choice specifically, we have 45 minutes for 35 questions. So it's a bit of a time crunch. We're going to go over the entire multiple choice set with this first part covering questions 1 to 17 and part 2 covering questions 18 to 35, completing the multiple choice set. So obviously, I won't adhere to the 35 questions or 45 minutes because I'm going to explain and walk through each of the questions, but I will go through the questions decently fast. And so if you do have any questions, leave them in the comments and our staff will further elaborate. So our first two questions are actually a pair. So we have that a ball is struck at time t equals 0 and follows the parabolic path shown in the diagram above. The following graphs show quantities possibly associated with the motion as a function of time t, which is speed, or rather velocity, I should say. Assume that air resistance is negligible and that the positive directions are upward and to the right. So which graph represents the horizontal component of the velocity of the ball? So this is a ball in free fall, meaning that the only force that acts on this is gravity. There's no force in the horizontal direction. So whatever velocity it had in the horizontal direction, it's going to keep that the entire way through. So we should have a constant velocity in the horizontal direction, which is shown by E. So one is going to be E. Next, which graph represents the vertical component of the velocity of the ball? So our velocity vector initially is going to be positive in the upward direction. Then when it reaches its apex, we're going to have that our velocity in the y, I should say, is equal to 0. And then at this point, right before it hits the ground, our velocity is negative. So we want to see something that goes from positive to 0, then negative, which is exactly what graph D shows. We go from positive, it hits the 0 point, then it goes down to the negative direction. So 2 is going to be D. Now we have question 3. An object with initial velocity v0 as shown above slides up and then down a long frictionless inclined plane. So which of the following is true of the object as it moves? So I wanted to draw just a quick free body diagram of this. We have the normal force that points perpendicular to the surface and the gravitational force, which always points downward. So when we really think about it, the thing that causes this object to slow down as it goes up the ramp and then it speed up when it goes down the ramp is gravity. Gravity is responsible for the motion of this object. We can even draw this into components, with this being FG, or rather perpendicular, sorry, and this being FG parallel to the surface. So Fn is going to be equal to Fg perpendicular. And then, so our net force is really this gravitational force in the parallel direction. And again, this is caused by gravity. Gravity is a constant, it won't change. And so that means its acceleration is going to not change. So we're going to see which one mentions constant acceleration the whole way through. So A, it has a constant acceleration while moving up the plane, and a greater, no. Its acceleration does not vary. It has a constant acceleration while moving up the plane and a smaller, nope. It moves up with a constant velocity both up and down the plane. Well, that's not true. It's going to slow down as it reaches the top, and then it's going to speed up when it goes back down. It has the same acceleration as it moves up and down the ramp, and that's what we're looking for. It's D. Now 4, excuse me. This is a hard question, honestly. So it says that two blocks of masses M1 and M2 are connected by a massless string that passes over a wheel of mass M. Now, this might seem insignificant, this over a wheel of mass m, but because the wheel has mass, that means we're going to have some torque involved. So we have a string, the string does not slip on the wheel, and it exerts forces T1 and T2 on the blocks, presumably tension. When the wheel is released from rest in the position shown, it undergoes an angular acceleration and rotates clockwise. This basically confirms the torque idea that we had before. So which of the following statements about T1 and T2 are correct? So because we're dealing with tensions, we can say that, or rather torques, we can say that torque net is equal to the sum of all the torques. And T1 and T2 both produce their own individual torques because they're applying a force on this wheel away from its center of mass. So if we know that it's rotating in the clockwise direction, we know that torque 2, the torque that this force is applying, has to be greater than the torque that T1 applies to it, because T1 is actually applying torque in the counterclockwise direction. So we can say that torque net is equal to torque 2 minus torque 1, because they're directed in opposite directions. And so again, in order for the pulley to rotate clockwise, torque 2 needs to be greater than torque 1. And therefore, the tension that creates torque 2, which is T2, has to be greater than the tension that creates torque 1, which is T1. They're the same distance away from the center of mass. And if we know that the torque formula is F cross R, if R is the same, then the force has to be different, meaning that T2 has to be greater than T1. And from the looks of our multiple choice, that aligns with answer choice E. It says that T2 is greater than T1 because an unbalanced clockwise torque is needed to accelerate the wheel clockwise, and that's exactly correct. Now we have 3 objects are located along the x-axis as shown above. The center of mass of the objects at x equals, or rather, the center of mass of the object is at x equals, and then it gives us the answer choices. So when finding the center of mass of something, we have to set our reference point. And so for this case, I'm just going to set my reference equal to 0. So we're going to take all of our masses into account. We have 3 kilograms. This is our mass 1. And it's 0 meters away from our reference point because it's actually there. Then we have our second mass, 5 kilograms, and it's a distance 3 meters away from that reference. And then finally, we have our third mass, which is 2 kilograms, which is a distance of 5 meters away from the reference. And then the total mass of all 3 of those individual masses is 10 kilograms. Simplifying this down a bit more, we have 15 plus 10 over 10 is 25 over 10, which simplifies down to 2.5, which is D. And you may have noticed I lost the units because on the multiple choice, it's not really important. You just want a numerical answer that'll satisfy the question. You're not being graded on your work, you're just being graded on the correct answer, unlike the free response. So now let's move on to number 6. Which of the following is equivalent to a unit of momentum? So we know that momentum is equal to mv, and this is kilograms times meters per second. But none of the answer choices are really conducive to that. So now I think of, well, how can we convert this to newtons or joules? Well, I know that F is equal to MA. And so this is, a newton is equal to kilograms times meters per second squared. Now to go from here to here, we just need to multiply by 1 second. That gets rid of one of the denominators in the, this gets rid of one of the seconds in the denominator. So we know that 6 is D. And also, many people, they refer to momentum as Newton second. So this might be something that you just look at it and it's like, oh, okay, it's a Newton second. Oh, I apologize. The arrow should be going the other way. But the same concept applies. So now we have number 7. 2 objects are dropped from rest from the same height. Object A falls through a distance dA during a time t, and object B falls through a distance dB during a time 2t. If air resistance is negligible, what is the relationship between dA and dB? So It seems like these objects are in free fall, so we're going to use the equation delta y is equal to vy naught t plus 1/2 a and the y t squared. They're both dropped from rest, so this term just goes to 0. So the equation that's going to govern both of them is just this 1/2 a y t squared. So for dA, we're just going to plug in the values that they give us. They don't give us an acceleration, so we're just going to leave it as a, and it says it falls during a time t, so this is just going to be t squared. And dB is going to be the same 1/2 ay. They don't tell us the acceleration, but they say it's during a time 2t squared, so this is actually going to end up being 1/2 a and the y 4t squared. And we want to know the relationship between dA and dB, which means we're going to have to set up a proportion where dA is over dB. So we're just going to put in the values that we got for that. We have 1/2 and the y t squared over 1/2 and the y 4t squared. A lot of these terms are going to cancel out. The 1/2 cancels, the a and the y canceled, and the t squares canceled. And we get a final value of 1/4. And answer choice A aligns with that. I will say when I was first doing this question, I did get stuck. I did choose D initially because I kind of just looked at these coefficients, or rather the constant blindly. And then I was like, oh, this has a 4, this doesn't, so it has to be D. But you need to remember the proportion part. So now we have number 8. The maximum mass that can be hung vertically from a string without breaking the string is 10 kilograms. A length of this string that is 2 meters long is used to rotate a 0.5 kilogram object in a circle on a frictionless table with the string horizontal. The maximum speed that the mass can attain under these conditions without the string breaking is most nearly, and then they give us a bunch of speeds. So this is a circular motion problem. So we're just going to set up our equation, which is the centripetal force is equal to mv squared over r. And now in this case, our centripetal force is actually just gravity because it talked about here in the beginning, the maximum mass that can be hung vertically from a string, which indicates that it's a gravitational force that allows the string to maintain that circle. We're just going to have Fg is equal to, well, our mass is 0.5. We're trying to find speed, and it says the length of the string is 2. And so Fg is just equal to mg, where m is equal to 10. We're going to make g equal to 10 as well. So this is just going to be 100 is equal to 0.5 b squared over 2. We're going to multiply that 2 over to get 200 equal to 0.5 b squared. Dividing the 0.5 on both sides, we get 400 is equal to b squared. And that b is ultimately 20, which is one of the answer choices. Answer choice D. Now on to 9. An object moves on a horizontal frictionless surface and makes a glancing collision with another object initially at rest on the surface. In this case, which of the following is true about momentum and kinetic energy? Now, just looking at the answer choices, I see them talk about conservation. No matter the situation, momentum will always be conserved. There's never a situation where it's not conserved. So anything that states otherwise is going to be immediately wrong. Like E is wrong, B is wrong because it's like momentum may be conserved. No, it's always conserved. Now, the trick is the kinetic energy part. So we're actually not given a lot of information about this collision. We're just told that it's a glancing collision, which just means that there's two objects that don't hit each other on their center of masses. We're not told explicitly whether it's an elastic or an inelastic collision, and quite frankly, there's no way to know. So we can't really say for certain whether kinetic energy is conserved or not. And so the safest answer here is to go with A, where it says kinetic energy may be conserved. We're going on the side of caution and saying that we're not sure. It might, but it might not. We can't say definitively that it will never be conserved or that it will be conserved. So now for number 10, a particle of mass m starts from rest at position x equals 0 and time t equals 0. It moves along the positive x-axis under the influence of a single force, F in the x is equal to bt, where b is a constant. The velocity v of the particle is given by, and then it gives you the answer choices. So this is our first calculus aligned question. So we're going to use our formula F equals MA, but we're actually going to rewrite A as dV dt. So we can rewrite the formula like this, and then just sub in what F is equal to, which is BT is equal to M dV dt. Now, in order to integrate, we want to use our separation of variables technique. We want to get the dV and the dt on separate sides. So let's work to do that right now. I'm going to isolate the dV dt term. We have bt over m is equal to dV over dt, and then I'm just going to cross multiply. So we have m dV is equal to bt dt. Now we can integrate both sides. I'm going to take out the constant term of the integral. So we have m times the integral of dV. And technically, there should be bounds of integration here. It would be v naught and v. But v naught, it said that it started at rest. Yeah. So we can actually just get rid of that and just have it be 0 is equal to b. That's our constant. And then we're integrating t dt. And again, there should be bounds of integration from t naught to t. But again, we're just going to set t naught equal to 0 just to simplify calculations. And now let's go on with the integration. So we have mb is equal to b times t squared over 2. There's no plus c or anything because of those limits of integration. It's an indefinite integral. So mb is equal to bt squared over 2. And then just dividing that m over, we get bt squared over 2m, which is answer choice B. Now for question 11. We have 3 blocks, A, B, and C, of masses 1, 2, and 3 kilograms respectively, which are initially at rest on a frictionless surface as indicated in the figure above. So you want to know what force F has to be applied on block C to accelerate the 3 blocks at 2 meters per second squared. So with this question, all of these blocks are kind of like smushed together. They're all joined. They're like conjoined together. And so for the purposes of this question, we're going to treat this as one system where all of these masses are going to be combined. So we want to know the net force F that has to be applied in order to move it at 2 meters per second squared. We're going to use our F is equal to ma equation. And again, because we're treating this as a conjoined mass, we're going to have 6 kilograms times 2 meters per second. That's our desired acceleration. And then just solving that simple multiplication problem is just 12 newtons, which ends up being answer choice E. Now question 12. An electrical motor provides 0.5 watts of mechanical power. How much time will it take the motor to lift a 0.1 kilogram mass at a constant speed from the floor to a shelf 2 meters above the floor? So I just want to draw this out really quickly. We start on the floor, this object, and then this is where our UG is equal to 0, and our kinetic energy is equal to some number that isn't 0. And then it like comes up to some like shelf. Let's just say that's the shelf where UG is going to be equal to MGH, and KE is equal to the same value here because it said it was at a constant speed, so those two terms are equal. So we know that power is equal to the change in work over time, or the change in time, I should say. And we know that work is equal to energy. So, whoops. So we can say that power is equal to the change in energy over the change in time. And this is really just looking at change in, This is really just looking at change of potential energy and change in kinetic energy. And since the kinetic energy is the same over the entire time interval, we're really only looking at the change in potential energy. So this is equal to UG final minus UG initial over some time, and the power is 0.5 watts. So 0.5 watts is equal to, well, UG final is equal to MGH. Let's actually substitute the values in right now. 0.1 Then G is just going to be 10. And then the height is said to be 2. And then we are already established that UGI, the initial potential energy, is just 0 all over a time that we're trying to find. And so that we get that 0.5 watts is equal to 2 over some time t, where t is equal to 4. That's what makes the equation true. So our answer is choice E. Now question 13. This one was tough, honestly. So we have that a block slides from rest with negligible friction down the track above, descending a vertical height of 5 meters, to point P at the bottom. It then slides on the horizontal surface. The coefficient of friction between the block and the horizontal surface is 0.2. And how far does the block slide on the horizontal surface before it comes to rest? So you actually want to separate this problem into two different stages. We're going to have before point P and after point P. So this is where friction is not present and where friction is present. And I just want to note at this point right here, at the very top of the hill, our potential energy is at its max and our kinetic energy is 0. And then at point P, UG is equal to 0 and our kinetic energy is at its max. And finally, it'll slide alongside this horizontal friction filled surface, and our UG is still going to be 0, and our kinetic energy is also going to be equal to 0 because it's allowed to come to rest, meaning that the energy at this point is also equal to 0. It doesn't possess any energy once it stops moving. So first, we want to find the speed of the object at point P. And since we've already established that at here, there's no kinetic energy, and at point P, there's no potential energy, and since the conservation of energy rules apply here, we can say that before point P, mgh, which is the potential energy at the top of the hill, is equal to the kinetic energy it reaches at point P, which is 1/2 mv squared. The m's cancel out, and so we have 1/2 v squared is equal to gh. Then we have multiplying the 2 over, we have 2gh. And finally, v is equal to the square root of 2gh. And we're just going to substitute our values in right now. We have 2 times 10 times 5, which is equal to the square root of 100. And so v is equal to 10 meters per second. Now we need to address this friction filled area right here. So we're going to set up our energy equation. We have our initial energy minus the work done by the friction is going to be equal to our final energy, which we already established to be 0 since it doesn't possess any potential or kinetic at the end of its motion. So that's just going to be equal to 0. And at point P, the only energy that it possesses is kinetic because our potential energy is 0. So it's going to be 1/2 mv naught squared is going to be our speed at point P. So I guess instead of naught, we're just going to put P squared minus the work done for friction. So that's actually just going to be equal to the force of friction times the distance traveled, which is what we want, is equal to 0. So we can actually simplify this further. So 1/2 mv squared minus Fn mu, because that's what friction is, times the distance is equal to 0. And then even further breaking that down, we know that Fn in this case is equal to Fg. So mg mu d is equal to 0. And now let's just plug in all of the numbers. So we have, or rather, let's simplify this a bit further. We have 1/2 mv squared is equal to mg mu d. We just moved this term to the other side of the equation. The m's cancel out, so we have 1/2 v squared is equal to g mu d. I'm actually going to rewrite that as v squared over 2. And then we can divide the g and the d over or rather the g and the mu over to get d is equal to v squared over 2d mu. And then I don't really have enough space to show the calculations, but you should get that d is equal to 25. Cool. So now let's move on to number 14. We have a graph above that shows velocity as a function of time for an object moving along a straight line. So for which of the following sections of the graph is the acceleration constant and non-zero? So I'm actually just gonna underline this as our motive. So we don't want the acceleration to be zero. So from point P to point Q, our velocity isn't changing. So our acceleration is zero. So anything that says from PQ, we're just going to eliminate immediately. So C and E are out. And the same goes for T to U. Since our velocity isn't changing, our acceleration is going to be zero. So we can also get rid of, actually C and E already encompass the TU part. So now I want to look at this segment QR. So you can see that it's not a linear segment. There's actually a bit of a curve to it. So the acceleration is going to be actually not constant. It's not going to be a single number. The acceleration is going to be different because you can put little different tangent lines there. So the acceleration at this point is something like that. That slope is going to be acceleration at that point. And then this is going to be acceleration at another point. You can tell that the slopes are different, meaning that the accelerations are going to be different during this time interval. So QR can't be part of the answer. So we can get rid of A. Now RS, this is going to be a constant acceleration because it's a linear line segment, and it's not going to be zero because it's not horizontal. It's going to be a negative acceleration, a negative constant acceleration. And same thing with TS, it's a linear line segment that isn't horizontal, so it's going to be a positive constant acceleration. So our answer is going to be D. Okay, now we have 15. The velocity of a particle moving along the x-axis is given as a function of time by the expression vt is equal to 3t squared minus 2t plus 4, where v is in meters per second and t is in seconds. What is the acceleration of the particle at t equals 2 seconds? This is just a simple take a derivative to get our acceleration function, which happens to be 6t minus 2, and then just sub in 2 into the function. And this is just 10. Which is D. Pretty simple question. You can even make this go a lot faster if on your calculator, on the TI-84 specifically. It may be different on other calculators. If you press math, then 8, then it brings you to this like derivative notation. Then you can just put in the function and then put x is equal to 2 seconds, and then it'll just pop out the answer choice 10 without having to do the derivative on your own. But it was a pretty simple derivative, so it's honestly whatever you prefer. So this is going to be the last set of questions that I cover in part 1. We have an unstretched ideal spring that hangs vertically from a fixed support. A 0.4 kilogram object is then attached to the lower end of the spring, and the object is pulled down a distance of 0.3 meters below the unstretched position and released from rest at time t equals 0. The graph of the subsequent vertical position y of the lower end of the spring as a function of t is given above, where y equals 0 when the spring was initially unstretched. And for 16, we want to know at which time of the following, or at which of the following times, excuse me, is the upward velocity of the object the greatest. So that was a lot of information, but we know that this is a graph of the position of the spring compared to time. This is y versus t graph. So if we want to know at what time the upward velocity of the object is the greatest, we actually want to look at the slope, because the derivative or the rate of change is going to give us the velocity. So we have our options from 0 to 1 second. So we can honestly just bound this graph off here. We're only going to be looking at everything to the left of it where the star is. So at time 0, Our slope is 0, so that can't be right. A is out. And same thing with 1. Our slope is going to be 0 at time t equals 1. And same thing with 0.5, actually. This is 0.5. So 0.5 and 1 are out. And so now we're just left with 0.25 and 0.75. Now at 0.25, we have a positive slope going that way in the positive direction. And at negative 0.7, or rather at 0.75, we have a slope in the negative direction. So the moment with the highest or with the greatest upward velocity is going to be B, 0.25, because it possesses the greatest slope of any of the points in the given time interval. And that makes sense because when we look at the y versus t graph, we can see that this point right here, this is our equilibrium point. It reaches equilibrium at this point, 0.25. It also reaches it at 0.75, but it's just in the negative direction. So, but when talking about upward velocity, it's talking positive. So 0.25 is assumed to be the greater velocity at that point. And now for 17, what is the spring constant of the spring? So for this, we can actually just go to our reference table. We can go to our reference table, and then we see that the period is equal to 2 pi, 2 pi times the square root of m over k, and we're trying to look for k. And so our period is 1 second, because that's how long it takes for the graph to go from trough to trough. I was trying to think of the term. You could also think of it from peak to peak, it takes 1 second. That's the period, how long it takes to go from minimum to minimum or maximum to maximum. It's going to be 1 second. And then we have 2 pi times the mass of the object. It's going to be 0.4 over k. And then if you were to do out the calculations, k comes out to be 16. For time purposes, I won't show it, but like you can just put it into your calculator, and it's just a simple rearrangement of variables. So that's going to be it for this video. In part 2, we're going to go over questions 18 to 35. So I will see you there. Have a great day.